two comments on this slide to begin with. First of all, you cannot have a whole afternoon devoted to the subject of Alan Turing without talking about Bletchley Park. It's like inviting people to dinner and then only serving them drinks. Your guests will go away unhappy and hungry because they know that Bletchley Park and Alan Turing are probably the same thing. In fact, it's not, it's a holy trinity of Enigma, Alan Turing and Bletchley Park. And you have to talk about all three or not at all. So that's why I'm here. That's why you've got a picture of Bletchley Park. But you will be asking yourselves, why has he put this absurd title saying Alan Turing's wasted years if he's going to talk about Bletchley Park? Well, this is a quote from Alan Turing's colleague, Jim Wilkinson, who had the misfortune to try and do numerical analysis under Alan Turing's supervision at the National Physical Laboratory some years later. And Jim Wilkinson was subsequently awarded the famous Turing Award from the Andrew, help me out here. Who gives this thing? The
Association of Computing
Machinery. Sorry, I always get confused because it's called the ACM Turing Award, and I'm thinking, no, Alan Turing didn't have a middle initial of C, so there we go. So it's ACM Turing Award. So Jim Wilkinson was receiving the Turing Award in 1970, I think it was. So of course, in 1970, nobody heard of this place, unless you haven't worked there, in which case you hadn't officially heard of it either because you weren't allowed to talk about it. So what Jim Wilkinson said was this, about the Bletchley Park years. He says, in the first place, there were 6 years starting from 1939, which he spent at the Foreign Office. And Wilkinson's complaining, because Alan Turing didn't write any mathematical papers, he only wrote 20. I think that's not enough. I'm saying, well, part of the problem is this period he spent working in the Foreign Office. He said, certainly it was there that he gained his knowledge of electronics. And this was probably the decisive factor in his deciding to go to NPL to design an electronic computer. That's quite interesting. He's not supposed to have known about that, is he? So curious. And then he goes on to say, mathematicians, that's you lot, mathematicians are inclined to refer to this period as the wasted years. So I'm going to talk to you about the wasted years. All right, let's begin with the next, well, the third thing in the Holy Trinity, which is not wanting to show itself on the screen. Thank you. We have a picture. Right, no, there we go. It is a picture. It's a picture of an Enigma machine. But the point is this. Okay. I do not believe for a second that German mathematicians believed that the security of the Enigma machine lay in these astronomically large numbers. But the problem is that with many code breaking and code making services, the two disciplines do not talk to each other. And while the code breakers in the various German services could have probably told the code makers that large numbers were creating nothing more than illusion of security, I think that the code makers, and in particular the senior army and other services figures that they talked to, believed that these numbers made the Enigma machine virtually unbreakable. If you ask Dr. Erich Hüttenheim, who was one of the senior German code breakers, what he thought about the problem, he would say, the Enigma machine in the Wehrmacht form, which is the version you've got a dim photograph of over there with the plug board on the front, is unbreakable if it's used correctly. I think he was probably quite right in that assessment of it. But he was assuming that people didn't do stupid things like put probable, predictable phrases in their secret messages. If you are going to send a weather forecast, send the word weather forecast, which conveys no secret information, in clear, because otherwise it becomes a code breaker's lever for prizing the cipher off the plain text. The technique of the probable word has been known by code breakers for at least 2 centuries, regardless of the type of cipher device that you are using, whether it's a machine, whether it's a hand technique, the device of the probable word may be your way in. Do not begin your Enigma message with the helpful phrase, "To the general, I beg humbly to report." That is conveying no secret information, and it is giving the code breakers the lever they're looking for. So use it correctly. And then there might be some safety in numbers. Here are some interesting numbers, and some of them have something to do with Enigma. I hope you enjoy them. Okay, it's not going to tell you how to break Enigma just by telling you that there is no safety in numbers. What we need is a technique, a system for finding a way around those huge numbers. We're not going to be able to devise a machine that is going to do a brute force attack on those very large numbers. What we need is some kind of logic test or some kind of inspiration to help us get to a workable answer. If you've got 158 million different ways of setting up the Enigma machine every day, I need to know how to reduce that search space to something that's actually manageable. This is where Wittgenstein comes in. I think Wittgenstein is an interesting influence on Alan Turing, because Wittgenstein and Turing, and I'm indebted to Andrew for explaining all this to me years ago. He doesn't realize he did it, but he wrote a book and it's all there. Wittgenstein and Alan Turing have this sort of interesting relationship where Wittgenstein is giving ostensibly lectures. He's not, he's really doing sort of graduate student discussion groups, and he's got Alan Turing sitting in the front row. And just as I'm picking on Andrew at the minute, he's picking on Alan Turing to talk about particular ideas and saying, well, Turing says this, and then of course Turing doesn't say that at all. But one of the things that Wittgenstein will ostensibly may have said at some point is that logic and mathematics can't reveal any truths if there are contradictions. And Alan Turing, of course, is at this stage in that process of his mathematical development where he is showing that mathematics, just like physics, is all fuzzy around the edges, and that there's no black and there's no white, and proof is a sort of an elusive concept. And yet there is still value in these half-formed concepts. The bomb machine, which is the invention that helps find, it doesn't find, it helps find the likely settings of the Enigma machine, isn't telling you a nice, clean, mathematically proven answer. What it's doing is weeding out a whole load of illogically impossible things if you happen to have chosen your probable word right. So what the bomb does, I'll show a picture of a bomb. I've got one on another page somewhere. There we go. You've got a whole load of Enigma machines all lined up. And what your bomb is going to try and do is test whether your probable word could have been correctly enciphered in the observed fashion at each of the chosen positions in the message. So in this case, this is an example taken from a book called Prof's Book, which is a TypeScript document written by Alan Turing probably about 1941, where he explains to new code breakers fresh from university who have come to join the Enigma team at Bletchley Park what it's all about. The mechanical method, the bomb. So he's chosen a probable word, in fact, probable phrase here, which is keine Zusätze zum Vorbericht, which I think might be correct by the German speakers in the audience. It means something like nothing to add to the preliminary report. Okay, keine, so you can see that on the second, it's actually the third line of capitalized TypeScript, keine Zusätze zum Vorbericht. And I'm sorry, it's got military abbreviation, so CH has been abbreviated to a Q. Fine. Okay, we can go with that. And then this is the observed ciphertext, the thing that they intercepted in Morse code in the airwaves. On the second line, they've lined it up to make sure that, as we all know, the Enigma machine cannot encipher a letter as itself. So you can just check that there are no mistakes in lining up our probable phrase with the intercepted text. And then what we've got is this marvelous machine where each of these trios of drums behaving like a trio of rotors in an Enigma machine is going to test whether, let's say, just take this one, A could encipher as I, and so forth. And then here's the clever part, we wire up these, connect up these fake Enigma machines using a wiring diagram, which is basically this thing here, which was called at Bletchley Park a menu. And we then run the machine, and then it stops at a point where it says, consistently, I have found a starting position on those three rotors. Bearing in mind each rotor's got 26 possible starting positions, so 17,500 in all possible starting positions. It will stop when it has found one plausible setting where all of those encipherments could have happened as observed. It's not telling you that's the answer. You might have got the wrong probable words. There might have been all sorts of things that have gone wrong with it. And typically the bomb machine will stop several times during a run because there are more than one possible answers even with that logic test. And of course it may be wrong. It's fuzzy, it's not clean, but it reduces the search space to something that's manageable. And I think that's quite interesting that he's moved right away from this idea that you can have a right and a wrong answer. It's just something that helps you get towards something that's within reach. And I think that's very clever. The really clever part of this I haven't got time for, but the really clever part of this is I've just reduced the search space amongst the 17,500 rotor positions. There's 150 million different plug board positions, and he's actually using a feedback mechanism, using electricity going into one wire and a 26-wire cable to help identify one of the cross pluggings, and one cross plugging is enough to blow open the entire plug board. That's very exciting. I would love to do a talk on that, but it's an hour's presentation and I haven't been given an hour today, and I've got to talk about other things. I've got to get myself back to Alan Turing's wasted years. Why are we talking about wasted years? Because, okay, you've all seen the Hollywood movie, or apart from him, no, he hasn't. You've all seen the Hollywood movie, and you know that because Hollywood tells you the absolute unvarnished truth, that Alan Turing sweated with his spanner in a garden shed for many years to produce this amazing device, and he produced it just in time to save countless American lives on the beaches of Normandy. How disappointing. This thing, the design for this thing was in the hands of the engineers of the British Tabulating Machine Company by November 1939. Britain was not yet involved in a fighting war in November 1939. By the time of the Battle of Britain, this thing was actually producing its first results, its first settings. Alan Turing was basically, he'll hate this, in retirement as a codebreaker by the time Britain came into a fighting war. Not completely, but his biggest achievement, his war-winning achievement, was all done before the fighting began. Unless you're Polish, sorry. Okay, so what did he actually do? We've got, I've still got sort of 6.5 years of war to go yet, and Alan Turing has retired. Well, he didn't quite retire. He actually moved into something which I think may have had, from a philosophical perspective, as big a contribution to the thinking about code breaking as designing this particular piece of machinery. You'll recognize some of these folks. You could do a sort of an odd man out thing on this, you know, which one is not a mathematician. In fact, some of them have interesting claims to be mathematicians, some of them don't. So there's Bayes, top left, you all got that. Fisher, top right, we all know Fisher, the great statistician. Friedman, probably not known to mathematicians particularly. Friedman being essentially the #1 code breaker for the US during the World War II period, and the inventor of something called the index of coincidence. Language is one of these interesting things, and it has curious mathematical properties. But if I encipher two completely different pieces of text using the same cipher, the frequency of letters, you might, when I encipher one piece of text using a cipher, particularly something like the Enigma machine, the frequency of letters is completely that you'd normally find in regular language. You know, E is the most common letter and Z's the least. That frequency inequality disappears completely. If I encipher two pieces of text using the same cipher, the frequency of letters in the two pieces of ciphertext changes subtly. And you can identify that the same cipher has been used by doing letter counts. So the index of coincidence, which is Friedman's idea, is sort of essentially a formalization of this thinking. This device, which is a punched sheet that was found in the renovation of Bletchley Park, it being stuffed in probably as a draft excluder. Bletchley Park huts were fairly primitive places to work. So this is probably just a used Banbury sheet been stuffed in to keep the draft out. What has happened is that an intercepted Enigma message has read HHCZH and so forth. So what they've done is they've punched out the letters that they observed in the Morse code onto this thing, and then they are going to do this with another message, possibly several, and then they will pile up the sheets on top of each other, and then they will look for places where the light shines through several holes at the same time, according to where you have aligned the sheets. This is telling you that the Enigma rotors are the same rotors in the same position. In other words, the same cipher is being used. It's exploiting this idea that the letter frequencies change if the cipher is the same. In other words, if the rotor positions are the same. This was very important for naval code breaking because the German Navy used a much more secure method for setting up their machines, which was not, it was not easy for the Bletchley Park code breakers to use the probable word attack because they didn't know what the German naval messages actually contained. Until you've actually broken some messages, you can't get any probable words. So you've sort of got a bit of a vicious circle. How do you actually do this? So this technique was designed to try and find a way of simplifying the rotor choice problem. It was actually thought of originally by the Poles in their attack on Enigma. It was called a clock method. And I think Alan Turing probably, having heard what all the Polish techniques were, adapted it using these punch sheets for use at Bletchley Park. So I don't say that he's responsible for this technique, which is called Bambarismus, but I do say that he encouraged the code breakers to think about probability, of which Friedman's index of coincidence is just one example, in an unorthodox and indeed probably mathematically illegal way as regards orthodox thinking stood in 1940. This is why I brought Fisher and Bayes into the picture. If you were a disciple of Fisher, you knew all about statistics, because statistics was all about things like normal distributions and chi-squares and Poisson and Prussian cavalrymen being kicked by horses. And if you don't understand that illusion, go and read some statistics textbooks, because they're all about Prussian cavalrymen. And being kicked by horses, not very nice. So I encourage you not to get too closely involved. Don't do any experiments of your own. But Fisher and Turing had history, because Alan Turing's dissertation for his fellowship at King's College, Cambridge, was not Sorry, Andrew, it was not actually about nail polish. His dissertation was about something called the Gaussian error function. How boring. Alan Turing had proved, without knowing it existed, something called the central limit theorem, which you all know about because you've all studied statistics. The central limit theorem, because Alan Turing hadn't bothered to study statistics, had been long proven, but he approached it completely from scratch and got there all on his own. And so the question was, could he be given a fellowship on the basis of second-hand work? Fisher gets dragged in by the Fellows of King's to opine on the quality of this dissertation, because obviously Fisher is Mr. Statistics. Professor R.A. Fisher's report. The subject chosen for the thesis is one which I have thought decidedly unattractive. Oh dear. Well, he got the fellowship, so that was all right. Fisher actually did say, I have no hesitation in judging Turing's thesis the work of a first-class candidate, so that was all right then. But the point is that Fisher would not tolerate anything other than traditional Gaussian style statistics. You take your sample, you measure it, and then you think about what that tells you about the population. You don't do it the other way around, where you guess about things and then try and work towards a more probable conclusion, which is the Bayesian approach to things. Alan Turing introduced Bayes back into the mainstream at Bletchley Park, subsequently championed by his assistant at Bletchley Park, I.J. Good, who, as you know, wrote quite extensively about Bayesian statistics in the post-war period and basically brought about its rehabilitation and practical applications. But its first use was really there at Bletchley, trying to work out which parts of the code-breaking problems were worth further effort. How do you improve the, when you're dealing with tiny fractional differences between one hypothesis and another, whether it's about sort of rotor choice or rotor position or something like that. It doesn't even need to be in the Enigma world. Lots of the hand ciphers had similar properties. How do we actually improve our understanding of what's worth further effort? Okay, and now you're puzzled because there's this person who's describing himself as a failed fruit fly geneticist, a failed lawyer, and now having a third go as a writer. And he's dared at the London Mathematical Society to come up with something that is not a partial differential equation. Okay, this is a code-breaking equation. This is about the problem of debt. So I was explaining to you earlier, if you'd enciphered two different messages using the same cipher, then you can find out all sorts of half-truths, which would have been proved of by Wittgenstein. X is my cipher, and I'm using modular arithmetic. It doesn't matter what base you're using, but the principle is basically the same. I've got two pieces of plain text, P1 and P2. I've got the same cipher, and so let's take a typical World War II Royal Naval code. They're using a code book. On page 11 of the code book, there is a 5-digit phrase, which is something like 69422. Right? 69422 might mean proceed from Devonport. Okay, and then there might be another code word that says towards Harwich or something like that. 69, whatever it was, 69422 means proceed from Devonport. I then add from another book, which has got my ciphertext in it, another 5-digit sequence using modular arithmetic, non-carrying arithmetic. Okay? So I've done that. Add or subtract, doesn't matter. So if it's a subtraction cipher, P1 minus X gives you C1, P2 minus X gives you C2. Code breakers are delighted if they can recognize that these two messages were enciphered using the same X, the same passage from the cipher book. they can actually figure out what the two plain texts are. You subtract the two messages from each other. You still get gobbledygook, but now comes in your probable word thing. We've heard this Devonport thing before. We know about that, or we can guess it from other intelligence. We can guess it from what a spy told us, watching the ships going in and out, that message must have been instructing those ships to proceed from Devonport. So we'll guess. We'll add back in the probable word, and then lo and behold, if our guess about the probable word was correct, the other piece of plain text will pop out as a clear answer. And you can do this for alphabetical ciphers, numerical ciphers, it doesn't matter. What you're trying to do as a code breaker is actually spot the cases where the same cipher was used. And so searching for depths was something that was a very important code breaking technique and critically dependent on this kind of probability analysis, the Bayesian probability analysis that was being championed by Turing and Good at Bletchley Park. They developed their own terminology for it. It's very interesting that GCHQ released Alan Turing's papers on probability analysis only in 2012, on the centenary year of Alan Turing's birth. Now, I find that astonishing because in code-breaking journals, people have been writing about Friedman and index of coincidence and Bayes' theory and all sorts of stuff for years and years and years. So quite why it needed to be kept a secret by GCHQ until 2012, I can't tell you. But I think that tells you that it was interesting and important enough to the way they go about their work for them not to feel comfortable with releasing it along with a load of other World War II papers in one of their earlier public releases. So I think that's quite interesting. The other interesting thing is that they haven't released it in physical form because they're terrified at the National Archives that people will steal Alan Turing original papers, and so it's only available online. Which I think is interesting, tells you something about Alan Turing and his importance, and particularly World War II. Okay, wasted years. When was this done? 1941. Alan Turing's papers, the ones that were released in 2012, were probably written in 1941. They've been dated by internal evidence. They're not actually dated, but you have to do a bit of sort of Bayesian statistics to figure out when it was done. But you can get that. 1941, September 1941. I've still got a lot of World War II to go. By 1943, oops, I got a shot. By 1943, we have really got to the end of the road with Alan Turing and Bletchley Park. They've tried putting him in charge of Hut 8. He's an absolutely hopeless administrator. It gets to the point where Hugh Alexander, who is his number 2, sort of by some Bletchley Park process of evolution, turns into Alan Turing's boss in Hut 8. I mean, I don't really know quite how that happened, but that's how it happened. That's what happened. And Alan Turing is sort of like becoming some kind of more dipping in and out kind of figure. He's brought in for particular problems. So he never quite disappears from the Bletchley Park scene. He's there in Gordon Welshman's machine committee, talking about and contributing, no doubt, to the debate on things like the development of Colossus, but he's not actually there. He's not full-time engaged with it. So they sent him off to the US in late 1942 to help the Americans, or rather, the agenda is slightly more subtle. It's to try and ensure British predominance over the Americans with regard to code breaking, particularly German code breaking, and that's all done under the umbrella of helping Joe Desch build a 4-rotor bomb for the 4-rotor Enigma machine, and it's also under the umbrella of, please will you check out the security of a new phone call encryption device that the Americans have invented with a view to Churchill and Roosevelt no longer being overheard on their transatlantic phone calls. Yeah, not a lot of people know this. the German post office had set up a listening station in the Netherlands, intercepting all the radio telephone calls between Churchill and Roosevelt, so they could listen in real time, because the scrambler system was so rubbish, they could descramble it quite easily and hear Churchill haranguing Roosevelt, which, I mean, I'm not sure that a great deal of strategic information was conveyed in those phone calls. So it was probably, I want some more destroyers, but it was sort of that kind of stuff, but which probably the Germans could work out for themselves. But it was definitely a security threat, and so this American device for encrypting phone calls became rather an urgent need. So he was sent over to check this out. When he comes back to the UK in March 1943, Alan Turing really sort of doesn't go back to Bletchley Park on a full-time basis. He goes to Q Division. You've all read the James Bond books, or if you haven't, you've certainly seen the movies. And you know that Q Division is where you develop the kind of pen that when you click it, it turns into a nuclear weapon, or you can poison your neighbor or whatever it is. Maybe they produce those things at Hounslow Park. It's still a secret what goes on at Hounslow Park, so I can't actually tell you. But during World War II, the goings on at Hounslow Park included something called the Radio Security Service, which has an interesting history of its own. And it was also the place where things like encryption devices were being invented. So Alan Turing turned from being code breaker into code maker, or at least the security consultant on code making devices. So that's going on at Hounslow Park. World War II photograph of the site there. It's where he meets his friend Robin Gandy, who Andrew was talking about earlier. So they both worked there together for a while. Alan Turing works on his own answer to the phone call encryption problem. Again, not really got time to do much detail on it, because that's another hour's presentation in its own right. So there's some photographs here taken from the report, which again is in the National Archives. The thing I think that's quite cute about this is that the change to the cipher that is through which the electrical signals that are generated by filtering the sound waves are, the encipherment is being done by this device here. And if you look carefully at that, it has a certain sort of familiarity of shape to it. That's not a coincidence. Alan Turing, always the practical person, thought, do you know what, when we're doing the cipher part of this, we should use kits that we have lying around. These aren't Enigma rotors, they're Type X rotors, but Type X rotors are the same thing. It's just that when the British ripped off the Enigma machine for their own cipher purposes, and they called their machine the Type X, it was an Enigma, it was a souped up Enigma. So this is basically Enigma rotors that are providing the cipher component to Alan Turing's voice encryption machine. Kind of cool. I like that. So that's kind of part of the answer to what was he doing during the wasted years. He was inventing this and doing the maths for it, which is good stuff. You want the maths? You can go and look at it in either the learned journal Cryptologia, which has got a reprint of the Delilah paper in it, or you can go to the National Archives and you can see the thing itself with the diagrams. All the blueprints are still there. Alan Turing did not do the blueprints. Don Bailey did the blueprints, because Alan Turing's handwriting, as we have seen many examples this afternoon, is completely terrible, and his typewriting was just as bad. Okay, one other thing about the wasted years, which I want to share with you, and this is not really written about much in the literature, and it's probably because the declassification process in the US has been very gradual and a little bit haphazard. The stuff is difficult to find. And I myself have only come across recently a bunch of papers about this, which I haven't been able to go and look at yet because of, you know what, we haven't been able to travel, and the US National Archives has been closed for 2 years. This is Madam X. Madam X was a Bell Labs project which Alan Turing was not allowed to look at. Why was he not allowed to look at it? Because when he went to the US in 1942, he had naval security clearance to help Joe Desch with the naval four-rotor bomb. He did not have US Army security clearance. And if you're British, you'd say, well, the dead security clearance, it's a security clearance, what's the problem? But the army knew who their navy was, their enemy was during World War II, and it was the Navy, and the Navy knew who their enemy was during World War II, and it was the army. So, I mean, clearly, naval security clearance is like the opposite of security clearance. It took about 2.5 months and pressure from the very, very most senior levels of the UK military in the US and none other than General George C. Marshall to resolve Alan Turing's security clearance problem so that he could see this, which is Madam X. I thought Madam X sounded really boring because it was the US Army bomb. Okay, well, we knew about the naval bomb. That's the clever Joe Desch thing, which has got electronics and it's got 4 rotors and, you know, it's sort of state-of-the-art engineering and it's very clever. So US Army bomb, well, you know, more bombs. I mean, I know what a bomb looks like. I didn't realize that the US Army bomb looks like this. It doesn't look anything like the rotary bombs that you can see at the one at Bletchley Park, for example, the National Museum of Computing. If you haven't been to see it, you should be ashamed of yourselves. Go and see the bomb. It's a cool piece of kit. You can also see Colossus there as well. Okay. What the US Army had done is taken away the idea of the bomb and then said, do you know what? We can completely scrap all the analog parts. We can scrap the rotary mechanical stuff and replace them by replicating them in switching. So what they did, because it's Bell Labs, they're the telephone company. What they did is they took boring, ordinary, off-the-shelf components that don't need to be made in a secure facility. There's no need to get people to sign the Official Secrets Act to make telephone relays. And they've got millions of them. So they filled rooms with telephone relays which were replicating in switching what a rotating bomb rotor does when it effectively switches an A into an X through electrical wiring. And it's kind of cute because with 3 banks of 3 relays, you've got 3 cubed equals 27 different outputs. That's a very neat number if what you're trying to do is to replicate the behavior of an Enigma rotor. Okay, I've got 3 banks of, I've got 27 relays that are replicating the effect of 1 rotor. You can imagine that they need rooms full of equipment to replicate in switching what Alan Turing's bomb machine was doing with wiring and rotating components. But what the clever part of this was, is that they could adapt it, they could reprogram it. Okay, it's not a stored program device, but what they could do is they could adapt this to do other problems. Whereas at Bletchley Park, what they had to do is to phone up BTM and say, we've got a new problem, we might need a new piece of kit. Could you put your engineers onto thinking how we might do that? They didn't need to do that with the US Army bomb. They just needed to create better algorithms and bring in a few more racks of relays. And I think that's very clever. And I think that's the reason why the US Army was so reluctant to let Alan Turing see this thing, because it represented his ideas for this analog machine. Okay, it produces a binary output, but it's basically an analog machine in completely digitized form. And I just wonder, I mean, I can't prove this at all, but I just wonder whether that acted on his mind in 1943 when he saw this thing, in order to help mature his own thinking about programmability. about what a real algorithm for a programmable computer might actually look like, how you might actually do it. At the same time, he's attending Gordon Welshman's committee meetings. And Gordon Welshman's committee meetings are not really about the development of Colossus. They are mostly about the punched card equipment, pre-war technology, pre-war digital technology that's being used and built by a British tabulating machine company in the UK. And this is a fusion of the really quite complex and interesting algorithmic approaches that business computing users were using before World War II, with this kind of idea that you could create your own problems and you could create your own switching structures to solve particular problems. And I think this is all working in his mind when he's thinking about what Andrew was talking about, and therefore is the appropriate punctuation point for my own talk. What became the work that he was doing in 1945 on designing that ACE. I think it's not the only flow, but it's one of the powerful influences in that piece of thinking. So I'd like to know more about the US Army bomb. There's a load of stuff that is now out there about it, but there's still these exciting 6 papers, one of which has only been recently declassified. I can't read them yet. I'm very disappointed about that. Anyway, thank you for listening. I hope you've enjoyed it. I hope you have enjoyed Alan Turing's wasted years.